Okay. Okay. So hi guys. Hello everyone. Hi. So hi everyone from YouTube. Hi everyone from Zoom classes. Okay. So today we are going to see a new topic called diffraction, right? So let me know if I'm audible clearly, YouTube guys. Okay. Yep. Good evening, Rekha Kumari. Okay. So hi everyone. Let me drop a message, right? Okay. Okay, it's cool. So let me have a very quick revision of what you have learned till the last class, right? So I'll be revising very quickly and we'll start and we'll move on to the new topic for today. Okay, cool. So till now we had almost 3 classes, right? In the first class of this chapter, we saw what an Huygens principle was, right? What an Huygens principle is, right? So Huygens principle says that, and it helps us to understand how to imagine light as a wave, how to imagine light as a wave, right? So that's Huygens principle, what we have learned in the first class. In the second class we have learned about constructive interference and destructive interference, if you remember. So we first learned what is superposition. Superposition is very simple. If there are two waves, so one wave and another wave, if they're getting overlapped on each other, you get a resultant wave, right? So this addition of waves is called a superposition. And in superposition, there's a special case, right? What is the special case? If these two waves which are combining have same frequency, if frequency of first wave is equal to frequency of second wave, right? And if they have same phase, if they have constant phase difference, if they have constant phase difference of or zero phase difference, then the superposition is called as interference. It is called as interference, right? And interference is beautiful, right? So if I have noticed, we get after when two waves from Young's double slit experiment. So we learned about Young's double slit experiment where the slit S1, slit S2. Light enters from S1 and light enters from slit 2. Okay, and these two light which are entering from the slit S1 and slit S2, they interfere. You can see that they're getting interfered here. After they interfere in this space, when they touch the screen, when they fall on the screen, I get a pattern, right? So what pattern do I get? I get at the center I get a bright fringe, central maxima. Then I get one more first maxima, at the top and at the bottom. I get second maxima at the top and I get second maxima at the bottom. Right. So this is what I do get. This was the interference pattern what we learned. And later on, after central maxima, I get a minima. First minima to the light to the top and to the bottom, and the second minima to the top here, and second minima to the bottom. And this kind of dark bright pattern is called as interference pattern. Interference pattern, right? Give me a second. Okay, so we have learned few things already here. So what are the few things which we have learned? We know what is the individual thickness of every fringe, right? How thick, what is the band width, or what is the thickness of a dark fringe, or what is the thickness of a bright fringe? We have calculated formula in the last class, right? And how far from the central maxima, how far the second maxima is located, or how far the third minima is located. So we have calculated many things. We have derived formulas in the last class. So among which I'll write very few important formulas. Okay. So height of the bright fringe is given as n lambda capital D by small d. Okay. And height of the dark fringe is given as 2n plus 1 by 2 lambda d by d, right? So where what is lambda? Lambda is the wavelength of the light which we are going to use for the interference experiment. What is small d? Small d is the distance between slit S1 and slit S2. What is capital D? Capital D is the distance between the slit and the screen, right? So that's the capital D. And what is n? So n are the number of the nth number of fringe, right? So I gave you a certain table for which fringe you have to use which n, right? So we have clarified yesterday. So remember this, okay? And one of the most important concept of last class was to get a bright fringe. The condition of two waves should be such that the path difference delta x should be equal to d sine theta, and that should be equal to n lambda. If the path difference between the two waves is according to this equation, then I'll get a bright fringe or a maxima. So this is the condition for a maxima. Or if the condition for minima such that the phase difference, or sorry, the path difference between two waves, which is d sine theta, is equal to not n lambda by 2, rather if it is 2n plus 1 by 2 lambda, then I get dark fringe, or I get minima, right? So these are the things which I learned in the last class, along with two small formulas, which is the width of the fringe. Fringe width beta is equal to lambda d by d. So all of the fringes, guys, here, the yellow fringe, the black one, all of these bright dark fringes will have same wavelength, same thickness, and that is equal to b lambda d by d. Okay, this unit will be in meters. So nanometers or centimeter or anything, it will be in meters. Okay, and one more thing, we also learned along with the fringe width, we have learned angular fringe width theta, which is nothing but lambda by d. So this will be in radians. How much is the fringe width getting exposed to, right? Cool, right? Okay, guys. So any doubts from this section? What you can see in the first screen here? Do you have any doubts? Zoom guys, YouTube guys, if you have any doubts, respond. If you don't have any doubts, click on yes. Okay. So then I'll be going to teach a new topic for today, which is called diffraction, which is the bending of light. Okay. Come on, guys, respond. Am I clear? No doubts? Okay. If you have any problem, you can let me know very quickly so that I can clear them out. If you don't have any issues, then fine, we'll move ahead. Okay. Cool, right? Yeah, that will be great. Okay, cool. YouTube guys, am I clear, right? I hope I'm clear. Okay, cool, guys. Sure. So moving ahead, we're going to see a different process of light called as diffraction. Okay, so uh, so we already basically know what is a reflection. You know what is refraction, right? Recently we learned interference. Interference is when two light waves meet, they constructively or destructively interfere and produce certain kind of pattern. That is interference. The fourth kind of phenomenon or the fourth kind of process which are going to say is called as diffraction. Diffraction of light. Okay, so what is this diffraction of light? If you have observed very carefully, okay, in Young's double slit experiment, so we take two slits. What are slits? Slits are very small cut in a paper, right? So there is slit S1 and there is slit S2. Okay, so what I'm going to do now, I'll be taking a planar wavefront. So I'm taking a planar wavefront, and this planar wavefront is moving normally. As soon as this planar wavefront passes through slit S1, what will happen? So this will be converted into spherical wavefront, right? So I've been writing the diagram in this particular way, right? Give me a second. I think UPS, get me UPS. Okay, yeah. So the light waves spread out from this point S1 to this point S2. Okay, so this point S2 will be So we're back again. Okay. So sorry for the trouble there. There was a power cut, and the laptop which I'm using has very low battery backup. As soon as the power gone, my laptop got switched off. Sorry for that problem there. Okay. So yeah, let me share you the screen and we'll begin the concept. Okay, we'll not make any further delay. Thank you for waiting there. Right. Okay. Thank you. It's awesome. Cool. Um, so let me share you the screen. Okay. Yeah. Okay, so here we are. So let us begin diffraction from fresh. Okay, so we'll start afresh. Okay, the first thing we need to learn. So I hope and I believe that all the concepts what you're supposed to learn from the last classes are clear to you, because nobody has any doubt and nobody asked me any doubt. So I believe and I assume that everything is clear. If you have any issues, let me know. Okay, and moving ahead further, so we'll try to understand what is diffraction. Okay, so diffraction to be um, told in a very simple words, diffraction nothing but bending of light. So refraction, right? So what is refraction? When light enters from one medium n1 to other medium n2, the light which is going in a straight line, it will bend, it will deviate, and this is called as refraction, right? This is called as refraction. So this is happens when we assume light as a particle also. Wait, and there is one more thing when we assume light as a wave, and whenever this light passes through very small slit, or whenever it encounters very sharp edge, even light bends at sharp edges. Light bends at sharp edges. Okay, and this bending of light at sharp edges, not from one medium to another medium, one medium to another medium is called as refraction. Bending of light at sharp edges is called as diffraction. So how does it look and how does it happen? So we're going to learn that today. Okay, so here I have a source, yes, which is emitting light, and in front of this source I have an obstacle. Okay, I have an obstacle which is like a regular cardboard, or it can be anything which is blocking light. Okay, it is not transparent, it is opaque. Cool, right? So when light starts from, and I have a screen very farther away from obstacle. Okay, so now light comes from source, yes, and it is traveling towards the screen. If there was no obstacle, the whole screen will be on, right? If there was no obstacle, the whole screen will be switched on here. This whole screen will be on if there was no obstacle. But here I have an obstacle now. Okay, so what's going to happen because of this obstacle? See, some of the light is blocked, this much amount of light is blocked here, and I'm getting a shadow, right? I'm getting a shadow here. From this point here to this point here, I'm getting a shadow. Very simple. But actually when I do this at a very small scale, and when these edges are very sharp, the shadows will not be this much, rather than shadows will be very much smaller. Only this much will be the shadow. Okay, there is a reduction in the area of shadows. Okay, see, next what's going to happen here is when the light was traveling from point S, and when it hits this edge here, right, instead of traveling straightly, it bends. Some of light bends and it is traveling in this particular path. Okay, and this bending of light at sharp edges, it where it started, it all started from this particular point, right? So here the diffraction starts, and this bending of light at sharp edges is called as diffraction. It happens whenever there are sharp edges all the time. Okay, this is simple as it is. Cool, right? So we call this region here, right? uh, X and Y, this region, this gray color region and this gray color region here, both sides, we call it as region of diffraction, because that is where diffraction is happening. Okay, and I've put in few statements what I've told you here exactly in words here, so you can use it for your reference. Okay, the encroachment of light, right? See, the light is entering the shadow region. It was not its territory, but the light started to enter shadow region. So when light encroaches from light part to the shadow part, that is called as diffraction of light. Okay, we can also tell it as, in a simple words, bending of light at sharp edges is called as diffraction of light. We could also tell in that way, it is not a problem. Cool, right? I hope the basic definition is clear. So we'll see. We'll perform a small experiment and we'll see how it looks. Okay, so here if you notice guys, I have a very small slit at the center. Okay, small slit, and the light is entering from the left side and it will fall on the screen at the right side. Okay, Now the light is coming from the left side here, right? And when the light passes through the slit, you can notice a wave form getting generated, a wavelet getting generated, a wavefront getting generated, and it's falling on the screen at the right? And when you notice clearly, so this kind of pattern you observe. Okay, so whenever you do this experiment, similarly, what I learned for the Thomas Young's double slit experiment, when we conduct this kind of experiment, we see this diffraction pattern. Okay, so very simple, right? So what was happening here? Very simple. So there was some wave coming from right side, from the left side, and it was passing through the slit. There was a very small cut here. There was a small slit here, and this light passes to slit. What happened to other lights? So all these lights are blocked because there is no slit. It's completely opaque. All the lights are blocked here. But the only way light can enter is through this small slit. Okay, and when the light is entering from this small slit, we expect the light to fall only exactly opposite to that particular point. But rather, if you notice very clearly, the light which is entering the slit is not just traveling straight line, rather than it is bending, right? The light is getting diffracted because if you notice slit is nothing but a very small sharp cut. When light touches these edges of the slit, it gets diffracted. Okay, and it's getting diffracted and it is bending its path, right? You can notice the ray diagram of the light, the sky blue one, right? So this is how we get the diffraction pattern. Okay, so let me ask you, what are the observations can you make? If we make the observations here, if you notice the central fringe is very large, very wide, if you compare to the black fringe or the other blue fringes, right? If you notice, this fringe is very large, right? It's wider than all other fringes. But rather than interference, if you notice, we had same fringe width everywhere. In almost all the points, we had same fringe. So central fringe, first maxima, first minima, second maxima, second minima, all of them were of same fringe width. All of them were same thickness in interference. But in diffraction, the central fringe is very wide compared to all the fringes. Cool, right? So, and you might ask, sir, okay, let it get diffracted, sir, let it bend, it might move away, and let me get a bigger pattern. But why am I getting a dark fringe, a bright fringe, a dark fringe, a bright fringe? Why am I getting such different patterns, that you might ask me? So for that, we do have an explanation, and we'll be seeing that very soon. Okay, so no worries about that. But I want you to be clear about this concept here. Okay, is the concept clear? I mean, through idea. I mean, are you conceptually clear about this concept? Can you understand what it is clearly? Yeah, I hope, right? So come on, respond to this or no. Or if you have any doubts, you can let me know. Okay, yeah. So feel free to communicate. You can tell me if you have any problems. You can tell me. Not a problem. So okay. So very simple. Light enters a small slit. It bends away. It's getting diverged, and it's creating a diffraction pattern. Okay. So now let us understand, why do I get the diffraction pattern and why do this occurs in the first place? Okay. So what I'm trying to do here is I'm taking a slit here, right? So there's a slit here from this edge to this edge. There's one slit, and a wavefront. Light waves are entering from left side. Light waves are entering from left side. And what do we believe? We initially believe that acha, all these lights which are coming in this particular region will be blocked. In this region they'll be blocked. Only this region light will be entering, right? So if I keep a screen here, only this much part of the screen must be illuminated. But that won't happen, right? But rather than, instead of this much getting illuminated, I'll be getting illumination for this much amount of distance, this much amount of uh, height, right? So that is called diffraction. So why it happens is very simple. Okay, so if you remember Huygens principle, when, see what's happening here, when the light enters this particular object here, all this wooden block is blocking all the light. Okay, and only where there was slit, the light is entering. Only this much amount of light is entering into the slit. And if you remember Huygens principle, Huygens told that every point on the wavefront, every point, you here also, every point on the wavefront will act as a secondary source. It will create one more wavelet, right? So again, so this happens all the time, and I get one wavefront here. And similarly, every point on this wavefront will act as a wavelet, and it will give rise to one more wavefront. We remember this concept, right? Same thing happens here. Okay, if you notice, every point on this red line which is on the slit will act as a secondary source, okay, and it give rise to a wavelet. So what will happen? So see, this wavelet is created here, and let me draw as many wavelets as possible. Okay, see, I've drawn as many wavelets as possible here. Okay, you can really easily see that the light which was supposed to pass only in this region, right, is now entering here also. See, the light is present outside that region also, right? See, initially I wanted the light to be only in this red region, but now if you notice, the light has traveled other regions also. Similarly, as you move ahead also, only you are supposed to make sure that light is only present in this red dot, which is in the same thickness here. But if you notice, the wavefront is getting stretched all over. It's getting stretched all over. And this bending of light due to Huygens principle is called as diffraction. Cool, right? Yeah. So this is extra, this red, black patch, right? This black patch, what you can see is the extra light which are getting due to diffraction. Okay. And I want you to observe one thing very clearly. So what's happening is, see, one wavefront from this source and another wavefront from this source is interfering here, right? See, you can notice they're getting interfered here. Some might get constructively interfere, some might get destructively interfered. So this interference between the same wavelets of a wavefront creates the dark fringe and the bright fringe on the screen. Okay, so we need to explain two things. Okay, from the diagram. First thing is, why is it bending? Why does it bend? Why does light bend? Okay, so am I clear, guys? Why does light bend? The light bends because we have to assume light as a wave. We should not assume light as a particle. We have to assume light as a wave. And this wave, this red one, which is here, will give rise to some other wavelets, and that wavelets are moving in this particular path. And if we draw the waveform, if we draw the wavefront for the spherical lights here, you can easily understand that the light is bending, it is going away also, not just it's going straight, it's bending away also. So that is one thing we need to explain, which we have explained already here clearly. So one more thing which we need to explain is very simple, okay, which is, why do I get bright fringe or maximas or minimas or dark fringe? Why do I get? Okay, so and that explanation is very simple. The one, the wave coming from the one wavelet and the other wavelet, they interfere. Okay, so they interfere, and due to this interference, we get bright and dark fringe. If you remember the last class of interference, same thing also happens here, and we do get bright and dark fringes. Simple. Okay, so are the two reasons clear, guys? Come on, respond with yes or no. Zoom guys as well as YouTube guys. Am I clear? Okay. If you respond quickly, I can move ahead very quickly. Okay. So I mean, you can save time by responding very quickly. Okay. If you have any doubts, respond no. I mean, see, I don't want you to sit quiet. Okay. If you are clear, you click on yes. If you're not clear, click on no. Okay. If you sit idle, that doesn't make any sense to me, right? Uh, okay. So you want okay, Nikita wants me to clear the first reason. Okay, very simple, Nikita. Okay, so if you think as a particle, if you think light as a particle, what will happen? If you throw a ball, this ball will pass through the slit, it will fall on the screen. You throw a ball here, this ball will hit this wall, and it will never pass inside, right? So when you're throwing physical objects like a marble or a ball, they'll only pass through these edges and they'll exactly fall on the top of the screen, on the side of the screen. But this is not possible if you can't explain this when you think light as a particle. Rather than you have to think light as a wave. Okay, when you think this light as a wave, when light is passing from the slit, right? See, so let me light as a different color here. So this was a slit here, and when light is passing through the slit, okay. So if I take the Huygens principle, I can get the clear explanation. So imagine now, I'll take this as one source here, one wavelet or one wavefront. What will happen? So from this wavelet, right, from this source, one more secondary wavelet is created, right? And this secondary wavelet give rise to one more wavelet, and this give rise to one more wavefront, right? So this is what's happening. Where you can see, right, the light which I assumed which will travel only in straight path, you can notice light wavefront is also passing outside that particular region of what I assumed to be initially, right? Similarly here also, if I take one more point here, this will give rise to one more wavelet and one more wavefront, and they keep on moving, and I keep on moving. So initially I thought that light will only pass through in this region, but if you can notice, light is passing in the other region also, right? So this is how we get diffraction pattern, diffraction. And why to get the pattern is because you can notice here two wavelets or wavefronts are combining, they're interfering, they're superposing themselves, and they'll give rise to bright and dark fringes consecutively. Okay. Is it better now? Okay. Okay, cool. So yeah, going ahead, let us derive some conditions. Okay, so what will the condition for a maxima there, and what will the condition for a minima there? Okay, so I'm taking same experimental setup. I'm taking a slit here. Okay, and a light is coming from left side to right side. It passes through the slit, and when it is passing through the slit, as I already told you, every point on the slit will act as a secondary source and give rise to wavelets, and wavefronts are formed. They they interfere and they create the pattern. Okay, at some point I'll be getting constructive interference, at some point I'll be getting destructive interference. That will happen all the time, everywhere, at many places. Okay, and this constructive interference and destructive interference will lead me to the diffraction pattern. Okay, will lead me to diffraction pattern. So at this region here, okay, if you notice, I'm getting a bright intense spot. So what's happening here is constructive interference. Okay, two wavelets from this part and this part are meeting here constructively, so I get a bright spot. And what's happening here, they're interfering destructively, so they cancel out and I get a dark spot. There is nothing, there is no light coming at that particular point, right? And that happens consecutively at all the places throughout the screen. Okay, cool, right? And only extra different difference from interference is that this central fringe will have more thickness than the regular fringe width. From interference, we have learned that fringe width was equal to beta, which was lambda d by d, right? It was constant for all of them, even for the central fringe, the first maxima, second maxima, all the minimas. I had a constant fringe width, but if you notice here, this fringe width is very high compared to other fringe width. Okay, and it was an experimental probe. Okay, cool. I mean, we can do it mathematically also, but I'm just telling you experimentally. Okay, we're not jumped into mathematics. We'll jump very soon. Cool, right? Okay. So now let us try to understand. Okay, what will be the location if I take this as the origin, as similar to what I did in interference. Now I'll try to find what is the distance of this fringe here. Okay, what is the distance of this fringe here, or necessarily not the distance. The distance is not important to me. What is the condition? What is the condition that I'm going to get a dark fringe here? Okay, I'll try to do that. Okay, and one thing I need you to tell here is, okay, for interference we had a solid proof. I mean, it was a uh, very good proof. Anybody can understand the proof, and it was very good. Okay, there is no fault in that proof. It was a 100% good proof. But one thing what's going to happen here is, for diffraction we don't have a solid mathematical proof for 12th syllabus. Okay, there is a good mathematical derivation for uh, diffraction also, but it is mathematically hard. It's mathematically hard. So what we're going to use, we're going to use a trick here. Okay, we're going to use a trick and try to devise the formula, or try to devise the condition. Okay, so remember, what I'm going to tell you is not a proof, rather than it's a trick to remember. Okay, so it is nowhere as close to the real proof. I mean, real proof is as clear as interference, but it is mathematically hard for us to prove it in 12th standard. So we'll just have a very small trick to find a condition, and we'll move ahead. Okay, and the condition is also pretty simple, but you have to understand it very clearly. Okay, so what's going to happen is, I have a slit here. The slit is spanning from L, ending at L. So the span of it is Ln. Okay, and what I'm going to do is, I'm going to consider a center point called M here, a middle point here. Okay, which is at a distance of a by 2. The total slit width is a here. Okay, the total slit width is a. Lm distance is equal to a, and I'm choosing a point at the center called M, located at half the distance. Okay, and there's screen. The screen is the distance of capital D. Okay, cool. The green light is entering from left side, and it is trying to pass through the slit. Okay, and we all know that initially the light was supposed to pass and hit the screen exactly opposite. Okay, but rather than exactly hitting the opposite side, it is bending. Light is bending topwards, downwards. It's bending everywhere, and this process of bending is called as diffraction, right? So what's going to happen if you remember interference derivation? So let me do that idea here. I'll not do the complete derivation of interference, but remember the derivation. Okay. So what will happen? Light from S1 will hit a particular point P. Light from S2 will hit a particular point P. Okay. All of these are making angle theta. Approximately they're equal. All of them are making angle theta, right? And if you notice, S1P is very small when compared to S2P. S2P is very long here. So what I did in interference derivation, if you remember, I dropped a perpendicular here. So when I draw a perpendicular such that this distance here is exactly equal to this distance. So what will be path difference? The path difference will be this distance here, right? This will be the path difference. Do you remember, guys? Remember this path difference, and this was theta. I proved you this also very clearly how this was theta. And by taking this triangle here, if this is theta, if this is path difference, and if this is d, if I take sine theta, right? What is sine theta? Sine theta is opposite. For theta opposite side is delta x, and hypotenuse is d. So x by d I get, and therefore d sine theta is equal to delta x. So this was a condition what we found out in the interference experiment. Okay. Imagine instead of d, if it was d by 2, if it was d by 2, this becomes d by 2 sin is equal to delta x. Very simple, right? It becomes delta x by hypothesis d by 2. So therefore it becomes d by 2 sin theta. Very simple. Okay. So same condition I'm going to do it here also, but I'll not do it for these 2 points. Rather than I'll do it for 2 points, any 2 arbitrary points between the slits which are located at a distance of a by 2. When 2 points are located at a distance of a by 2, I'm going to assume that one light from this point L, okay, and one light from this point M, those 2 light waves are going and hitting the screen at a point P. They're going and hitting a screen at point P, and what will happen? They'll interfere. Okay, so now I want to find the condition for dark fringe. Okay, I'll do the reverse. Initially, in interference, I did it for the bright fringe first. Here, I'll do it for the dark fringe. Okay. So since I'm taking these 2 as the source, this point and this point as the source, okay, this distance here, this distance here is a by 2. Okay, and between these 2, this will be the path difference delta x. Am I clear? If you this distance will be equal to this distance, they cancel out. They cancel out without any problem. Okay, and extra distance, what I'll be left with is the path difference delta x. Okay, and this will be theta as similar to the interference experiment I've told you, and this will be 90-degree. Okay, so am I clear till now? Any issues, guys? Any issues till now? Okay, if I've understood, click on yes. If you've understood, click on yes. Okay, same thing, right? What I did was in interference, I took 2 sources coming from S1 and S2. They interfere at some point, but here in diffraction, I'm considering sources which are coming from only one slit, but 2 different sources, 2 different points. Okay, cool, right? So, and this will be the path difference, and this is the a by 2. So if I write the triangle here, if I write that triangle here, this will be theta, this will be hypotenuse, this will be d by 2, and this will be the path difference delta x. So what is sine theta now? Can anyone tell me what will be sine theta now? Let me see who will tell me the quickest answer of sine theta. Yeah. Come on, guys, quick. So what will be sine theta for this triangle? For this triangle here. Okay. So opposite by hypotenuse. What is opposite? Theta opposite is delta x, right? Sorry there. That's correct, Nikita. Good. Okay. So theta, sine theta will be equal to delta x divided by the hypotenuse is d by 2. Oh yeah, that's right. And therefore, what I'm going to do is I'm going to take this d by 2 to the right hand side. D by 2 will be at the right hand side. Sine theta will be there itself is equal to delta x. So therefore, the path difference here will be equal to d by 2 sine theta. In interference, I got d sine theta because the distance between 2 sources was d. But now if the distance between both of them is d by 2 or a by 2, it becomes a by 2 sine theta. If it is d by 2, it becomes d by 2 sine theta. Since I've taken a here, let me use a everywhere. Okay. So a sine theta is equal to delta x for interference, but here it will be a by 2 sine theta. That's correct, Ramakrishna. Good. Okay. And Nikit also good. That's great. That's great. Okay. So moving ahead very slowly. Okay. So this is the condition what I get from the trigonometry. No problem. Very simple. Okay. So therefore, the path difference delta x should be equal to a by 2 sine theta. this is the path difference all the time. Okay. So now if I say that I'm getting a dark fringe, okay, if I'm getting a dark fringe, can you tell me guys what will be the path difference for the dark fringe? Take the first fringe, take the first dark fringe. Okay, so how do you get a dark fringe or destructive interference? So one wave is in this particular way, and when one more wave is in this particular way, right? In this case, I'll get destructive interference, if you remember, right? So the see now the peak will meet the crest will meet the peak, they cancel out. Now, can you tell me what is the path difference for these two waves now? What will be the path difference? This delta x here. What is the path difference between these two waves I'm writing here? Come on, guys, who will tell me quick? Let me see. That's correct, lambda by 2, right? I'm talking about path difference, path delta x. Okay, it is lambda by 2. Okay, so always remember path is distance. You have to you have to use lambda for distance. For phase, it is angle. You have to use pi. For angle, you have to use pi, right? So if you notice the difference, this is 0 degree, this is 90 degree, this is 180 degree. Therefore, the phase difference between these two is pi, right? If you remember, the phase difference is pi. Right, you have to remember the old condition. For 0, 2 pi, 4 pi, 6 pi, I get bright fringes. For pi, 3 pi, 5 pi, 7 pi, I get the dark fringes. Right, so you have to remember the condition also. And the path difference is half of the wavelength. If you notice, this one is a complete wave here, from here to here, but I have only half wave here. So the path difference is lambda by 2. The path difference is lambda by 2. Bas, ho gaya. Okay, what to do is, for dark fringe, therefore the condition will become half and half cancel out. What are left with? A sine theta is equal to lambda. Generally, I can put A sine theta is equal to n lambda. Cool, right? Oh my God, how is it possible? So I took for condition dark fringe, and I'm getting the condition for bright fringe of interference. Right? The formula is getting reversed. In interference, this condition was for bright fringe. Do you remember, guys? I hope you remember, right? So this was a condition for bright fringe in interference, but in dark fringe, it is for diffraction. It is for dark fringe. It's getting reversed. Okay, so I'll do it all again from the beginning very quickly. Pay attention. Okay. So see this red color mark is the path difference between the light coming from S and light coming from N. Okay, and if you do the triangle part here, which I taught you very clearly from last 2-3 classes. Okay, so this will become theta, this will be perpendicular which I'm dropping, and this will be delta x, and this is a by 2. If you check, if you just put sine theta formula for this triangle, you will get that the path difference delta x is equal to a by 2 sine theta. Okay, and I've told you that the condition is I'm going to consider dark fringe getting at some random point. So I have to put the condition for dark fringe. Okay, therefore I liquid the path reference a by 2 sin theta to lambda by 2. So why there is plus or minus lambda by 2? So plus lambda by 2 is for the upper fringe, minus lambda by 2 for the lower fringe. That's all, no difference. Okay, so I'll equate it to minus plus or minus lambda by 2. Plus is for above 1, minus is for below 1. Okay, what happens now? By 2 cancels out. I'll be left with a sin theta is equal to lambda, or generally what happens is a sin theta is equal to lambda or n lambda. So this is a condition for dark fringe. This is a condition for dark fringe. Okay, am I clear, guys? Okay, so let me make it much more clear. Let me make it much more clear here. Okay, what's going to happen is, see, when I take one point which is at L and one point which is at M, and they're a distance of a by 2. So both of these are a distance of a by 2, right? So they will meet and they'll cancel out. So what about other wavefront? You might ask me, sir, you can only consider few points. What about other points, sir? So what happens is, I'll consider one more point here and one more point here, and now both of their distance is also a by 2. Okay, when the distance is a by 2 and the path difference is lambda by 2, they cancel out. So nothing comes again from this red color points also. Again, I'll choose one more point here and one more point here, which are a distance of a by 2. Okay, they satisfy this condition, they cancel out. I won't get any fringes, right? Similarly, I'll choose one more point here and I'll choose one more point here. They'll again meet at a distance of lambda by 2, they cancel out. And lastly, I'll choose this point here and I'll choose this point here, which are again the distance of d by 2. They're going to satisfy this condition because their phase difference is a by 2, so their path difference is a by 2 sin theta, and their path difference was lambda by 2. So when I equate these two now, I get dark fringe. They cancel out. All this point which are at a distance of a by 2 cancel ho jayega, and I'm left with a dark fringe at that particular point. Okay. Am I clear, guys? Am I clear? So respond with yes or no. Very simple. Okay, so very simple. So it is not a real proof. It's not a real proof. It's just a trick to solve. So I have to remember the trick here. What I'm going to do here. Okay. So if you want to derive the condition for dark fringe, you would choose any 2 points which are at half of the distance of the total slit, and you put the condition for dark fringe as lambda by 2 path difference. You equate it. You'll get a set is equal to n lambda. All the points which are at a distance of a by 2 will cancel out and will give me a dark fringe. Okay, am I clear, guys? You want me to repeat again, or am I clear here? Okay, I mean usually this confuses students much, but I hope you get it. And if you have any doubt, let me know. There is nothing in that. Okay, feel free to ask me again. Okay, cool, right? So therefore, every point which are at a distance of a by 2 will cancel out, and you'll be getting a dark fringe. Okay. So and here I have written the general condition a sin theta is equal to plus or minus n lambda by 2. Okay, so this will be the condition. Cool, right? So whenever two waves of the same wave front here meet this condition, they're going to interfere destructively and they'll give me a dark fringe. And I hope you're clear by now. Okay, therefore, see, let me write an interference formula. For maxima, the condition was d sin theta is equal to n lambda. For minima, the condition was d sin theta is equal to 2n plus 1 lambda by 2. Right. So now what's happening for diffraction? For diffraction, what happened was, see, for maxima, it was n lambda by 2. Sorry, n lambda is equal to d sin theta. But here, that is the condition for minima. For minima, I'm getting d sin theta is equal to n lambda. Therefore, I hope you can assume that for minima, which was d sin theta is equal to 2n plus 1 lambda by 2, that will be maxima here. So d sin theta will be equal to 2n plus 1 into lambda by 2. The conditions will be reversed. Maxima and minima conditions will get reversed out. Okay, and again, I'll show you that what's going to happen. Okay, I'll show you this condition also. But you can easily understand the formulas in interference and diffraction are opposite. One for maxima will be the other case, it will be minima. Cool, right? Okay, so now let us try to understand. Okay, how do I get the bright fringe? How do I get a bright fringe? Okay, so now again I'm going to assume the same condition. There is a slit of width distance a. Okay, and now initially I took points which are at a distance of a by 2. Now what is the next integer? A by 3. So I'm going to consider two different light sources which are at a distance of a by 3. Okay, so that means this distance is a by 3, this distance is a by 3, this distance is a by 3. You add all of them, a by 3 plus a by 3 plus a by 3. What do you get? A by 3 plus a by 3 plus a by 3 is 3a by 3 or a. So therefore the total width will be equal to a. So there is no difficulty in this, right? Yeah. So now a light wave is entering from left towards right, and I believe that it has to only pass through this blue color dotted lines. But no, the light will move everywhere. It goes to the top side also, it goes to the bottom side also due to diffraction. Okay. So now I'm choosing a point P randomly where this one light from L, other light from M dash, which are at a distance of a by 3 are meeting. Okay, these two lights are meeting at this particular point. Okay, so now again if I put one line here, perpendicular line, if I take the path difference. Okay, now tell me guys, what will be the path difference very quickly? When there is no need for you to do the triangle again. When the distance between the slit was d, you got d sin is equal to d sin was a path difference. When the distance was d by 2, you get d by 2 sin as a path difference. Now the distance between the sources is a by 3. So you can easily understand that the path difference will be equal to a by 3 sin theta. Right? Interference experiment, d sin theta was the path difference. In the previous experiment here, which we learned, in which the sources were at a distance of d by 2, then I get a condition of a by 2 sin theta. Right? Now the sources are at a distance of a by 3. Therefore, again, if you put the triangle here and the right angle triangle, if you take the hypotenuse and you take the sine angle, you'll get delta x path difference is equal to a by 3 sin theta. Clear, right? Okay, cool. So now again I'm going to use one more small trick here. Okay, I'm using lots of trick, but forgive me, there is no other way. So I'm going to use one more small trick here. Okay, so two light waves coming from L and M are meeting at point P, and I'll tell you that they have path difference of lambda by 2 again. Okay, they again have a condition. I'm just assuming this condition. They have path difference of lambda by 2. So what will happen now is very simple. Okay, the path difference was a by 3 sin theta, as already told you. Okay, and whenever they have lambda by 2 phase path difference, always remember when one wave is in this particular way and when one wave has a path difference of lambda by 2, what will happen when these kind of wave meet? They destructively interfere, they cancel out. Okay, so even though I'm deriving for bright fringe, I'll make sure that they have the distance of lambda by 2. This L wave will cancel this M dash wave because they're at a distance of lambda by 2. They cancel out, they cancel out. Okay, cancel ho gaya, cancel ho gaya. So now what will happen? So very simple, very simple. I'll take one more point here, which is at some distance, and I'll take one more point here at which is some distance. Difference between these 2 points is a by 3. So these 2 points will meet again, and they'll give me destructive interference because they're at a by 3 distance, and the path difference between those two is lambda by 2. Okay, and same thing I'm going to do it again. I'll take one more point here, and I'll take one more point here again, which are at a distance of a by 3 and having a path difference of lambda by 2, they again destructively interfere. So if you notice, all the points between this region is already occupied by me, but this region I have not yet started. This region is completely left alone. It is idle. There are no more points at distance of a by 3. All of them have lesser distance. If I take any 2 points, they'll be having lesser distance than a by 3. So what will happen now? This a by 3 part distinctly interfere with this a by 3 part, they won't give me anything. It was a dark fringe. But this a by 3 part will give me the light. This a by 3 part will be responsible for the bright fringe. Okay, cool, right? So I'll again tell you, not a problem. Okay, so for every point which is at a distance of a by 3, they'll interfere because they have a distance of lambda by 2. They cancel out, and I'll be left with. Okay, see, I'm doing that here. M1 and M2 are distance of a by 3. They every point here they meet. Okay, and they cancel out. They cancel out, and what I'm left with is just this part here, and that will be responsible for the bright fringe. Okay, and if I solve this solution here, okay, let me solve this equation. The path difference delta x from the triangle was a by 3 sin theta, and the path difference I assumed. Okay, I gave a condition that if light waves meet at lambda by 2, they destructively interfere. Okay, so then a sin theta is equal to, what do I get? I get 3 lambda by 2. Okay, so or 3 lambda by 2 can also be written as a sin theta is equal to 2n plus 1 lambda by 2. See, this is the condition for bright fringe in diffraction. This is the condition for bright fringe in diffraction. Okay, I hope I'm clear. Okay, so you can write that formula as I written here. Instead of writing 2n plus 1 by 2, you can divide 2 in both the sides and you'll get this simple formula here. Okay, so before asking you whether it is clear or not, I'll give you one more idea. Okay, so in diffraction, what we do is we don't have a solid proof. Rather than we're going to use numerous tricks to understand and derive the formula. Okay, so here I'm going to derive for dark fringe, and here I'm going to derive for bright fringe. Okay, so what happens here in this case is when light enters, okay, if the light sources, I mean, see, I was already told you, if there is a wave, every point on this wave will act as a secondary source, right? I'm choosing two sources which are at a distance of a by 2. And what will happen? When sources are of a by 2 distance, their path difference will be equal to a by 2 sin theta. And if they have a phase difference of lambda by 2. So for example, this wave and this wave meet somewhere, they are going to meet here. And if they have lambda by 2 distance, what will happen? Whenever you have lambda by 2, they have to cancel out because one wave is in this particular shape and other wave will be in this particular shape. They have a path difference of lambda by 2. They'll cancel out because lambda by 2 difference, they have to cancel out, and you'll get a dark fringe here. Okay, and similarly, if I take all the points which are at a distance of a by 2, see, I keep on doing, I keep on taking the points, I keep on taking the points. All the points which are at a distance of a by 2 will cancel out, and I'll be left with a dark fringe. a complete dark fringe. And 2 cancels out here, and I'm left with A sin theta is equal to n lambda. This is general condition for dark fringe in case of diffraction. Okay, same thing we'll do for bright fringe also. But for bright fringe, since I've already taken half integral here, I'll take a by 3. I'll divide this into three parts: a by 3, a by 3, and a by 3. Okay, so what I'm going to do is I'm taking one source from this point, and I'm going to take one source from this point. What's the distance between these two? A by 3, and phase difference, sorry, the path difference will be equal to a by 3 sin theta. And I'll tell you that again, I want both of them to cancel out. Okay, I want both of them to cancel out. So I'll put the criteria as, let these two distinctly interfere such that the path difference between them is lambda by 2. They cancel out and I get dark fringe. Here also I'm getting dark fringe. Okay. So when these have a by 3 sin theta and the path difference is lambda by 2, they again cancel out. Okay. So let me do the same manipulating here. So the points which are at a distance of a by 3, they distinctly interfere, they cancel out. The distance which are at a by 3 points, they cancel out. Okay, they cancel out completely fine. So this upper a by 3 is cancelling out the lower a by 3. You can notice, right? And if I try to cancel out the remaining a by 3, I can't cancel it. Because if one point, if I choose here, the other point will be here, but there is no wavefront coming from this particular point. So this a by 3 will not interfere at all, and this light will pass here. Okay, and this will give me the bright fringe. This will give me the bright fringe. Okay, and this proof can be done for any number of distances, not just a by 2. You can consider, instead of a by 2, you are free to consider a by 2, a by 4, a by 6, a by 8, a by 10. If whenever you choose even multiples in the denominator, you always get dark fringe. You always get dark fringe. Okay, and whenever you take the distance of a by 3 or a by 1 or a by 5 or a by 6, sorry, a by 7 or a by 9, you get bright fringes. Okay, because here 2 parts will cancel out and 1 part is contributing for the interference. Here 4 part will cancel out and 1 part will contribute for interference for bright fringe. Here 6 parts will cancel out and 1 part will contribute for diffraction. Here in a by 9, 8 parts will cancel out and 1 part will contribute for diffraction. Okay, so this is how happens. Okay, I hope you're clear with the idea, but I want you to understand this criteria. The criteria will be reversed. So for dark fringe, A sin theta is equal to n lambda is a criteria, and if I send this 3 here, and then the general condition can be written as 3 by 2 lambda is nothing but 2n plus 1 lambda by 2. Okay, so this will be a condition for maxima, bright fringe in case of diffraction. Am I clear, guys? Am I clear? Respond to yes or no. Did you get some idea? Did you get some idea? I hope you get some idea. Okay. If you respond quickly, I'll move ahead. We can solve some problems, and we'll see what is the pattern of this interference. We'll try to get some practical application. Okay. Yeah. Okay. Cool then. Cool. So moving ahead very slowly. Yeah. So those are two things which are derived. And if I remind you from interference concept, where, give me a second. Let me draw one line. Yeah. So I got it. Yeah. So if you notice the intensity of the interference pattern, so this is the graph of intensity, this is the graph of distance. In interference, all the fringes were like this, right? The central maxima was of the same width as of any minima or of any maxima. They have same widths all the time, and all maximas have same intensity. All maximas have same intensity, same width, and all minimas have same width but zero intensity. They'll be dark. And how does this graph varies for um, diffraction? So when you do this experiment, and if you notice, when you plot intensity versus angle or distance, you'll get this kind of a graph. Whereas for interference, you get this kind of a graph, right? But for diffraction, you get this kind of a graph, which is saying that the central fringe is very, very wide. The central fringe is wider than other fringes, and therefore they check the intensity. It is also brighter than all other fringes. It is also brighter than all the fringes, right? So, and what is the formula? Again, there is no derivation here, okay, but the fringe width for maximas and for minimas will be equal to lambda d by d, the same formula what we derived for interference, but with one exception. Okay, the fringe width for central maxima, because central maxima is very large if you compare and if you see here. So therefore, central maxima will have a fringe width of 2 lambda d by d. Okay, it will have a distance of 2 lambda d by d. It is twice the thickness of the other fringes. It is twice as thick as other fringes. Okay, am I clear, guys? Okay. Okay, right. So very simple. You have to remember this. Okay, all the fringes will have a width of beta, which is equal to lambda d by d, and the central fringe will have a width of 2 lambda d by d. It is quite wide. If you notice in the diagram also, it's quite wide. So this is the formula you get when you do the mathematical calculation and all. Okay, and intensity is very bright. The intensity of this particular light is very high. So therefore, I'll be getting brighter central fringe. And this is true. Why it is true? Because see, imagine I have a small cut here. I have a paper here. Okay, and in this paper I have a small cut. When light is passing through small cut, most of the light will fall at the center. Only little bit is getting diffracted. Right? Only little bit will be getting diffracted. So that is why the same thing is also happening here. Most of the light is only at the center. Only few amount of light is getting diffracted. Same thing. It's true also, right? That is what practically we also see. And you can see this very clearly in a cricket stadium. So if you have noticed while watching the cricket, when they have a cricket stadium and during a one-day match or a night match, they'll put this huge floodlights, right? When they put the huge floodlights, you can notice the shadow. The shadow of the player will not be just one shadow, rather than he'll be having multiple shadows, right? He'll be having multiple shadows, right? You might have noticed. I mean, you might have noticed in your place also, in your villages also, or in your town also, where in the city square they'll put huge towers and they'll put 4 5 white LED bulbs to shine the whole area. And if you go and stand there, you can see your multiple shadows because of every individual bulb, and all the shadows are not sharp. For example, if your shadow was supposed to be in this particular dark patch, in this case your shadow will be dark in the middle and it will be lighter outside. It will be light shadow outside. The light is getting encroached, the light is trying to come inside the shadow, and this is diffraction what you usually see in the real life. Okay, I hope I'm clear, right? Yeah. Okay, so let me give you some questions. Okay, then I'll move on to a concept of polarization, which is again an important concept. So let me give you some problems, 2 or 3 problems, then I'll move on. Okay, so now remember, a parallel beam of light of wavelength 4000 Armstrongs gets diffracted by a slit width of 2 millimeter. What is the angular position of first minima? Okay, so they're asking me the angular position or angular fringe width. Angular fringe width is theta. And what are they asking me for? They're asking me for minima. So what is the condition for minima? For condition for minima is d sine theta or a sine theta is equal to n lambda. So remember, this is minima in case of diffraction. Okay, maxima in case of interference, and this is the minimum in case of diffraction. So they're asking first minima, so I put n is equal to 1, and I can put sine theta is equal to theta, and lambda there itself I'll bring d to the denominator. Bus. Oh yeah. Therefore, wavelength is 4000 Armstrong. That is 4 into 10 raised to minus 10 divided by distance between the slits is, okay. Our slit width is 0.2 millimeter. 0.2 millimeter, or this becomes 4000 into 10 raised to minus 10 divided by 2 into 10 raised to minus 4. Okay, so 3 zeros I can cancel here. I'll make it 3 7 here. Okay, instead of 10 I can make it 7. 4 zeros I'll cancel here. I'll make it 3, or I get 2 millimeter. So 2 millimeter will be the answer. Cool, right? Sorry, not 2 millimeter, 2 radians. Sorry about that. Okay, I mean, because angular fringe is not having any unit of meters but of radians. Cool, right? So this is a condition for first minima. You have to use the formula d sine theta is equal to n lambda. Diffraction minima. Diffraction minima. Okay, use the formula. Cool, right? Yeah, hope I'm clear. Okay, so going ahead with one more problem. it is again, it's simple. You try to solve it, okay, with me. A single slit width of A. So there's a slit width of A is illuminated by a violet light of wavelength 400 nanometer. So in one case, what they're doing is they're taking a slit width of A, and the wavelength they are going to use is 400 nanometer. This is violet. Okay. And the width of central fringe of the diffraction pattern is measured as y. So at the center, they're going to get a central fringe, and that width is y. So I'll put y of violet color. Okay, so when I use violet color, I'm getting a central fringe width of distance y. Okay, no problem. Now, what are they going to do? In the next case, they're going to cover half the slit. When half the slit, so this was the whole slit, I'm covering the half of the slit, so I'm left with a by 2. So when half the slit is covered and illuminated by an yellow light, instead of using violet light, now they're using yellow light. Okay. Then which has a frequency, sorry, wavelength of 600 nanometer, then the width of the central fringe of the pattern will be. So what will be the width of central fringe in case of yellow light? They're asking the value of the thickness of yellow fringe, yellow central fringe in terms of violet fringe. So simple. They're given two conditions. Write it down very clearly. So what is the fringe width of central fringe? Central fringe will have a fringe width of 2 lambda d by d. Am I clear? So simple formula, write it down. So there are two situations here. One is for the violet light, another for the yellow light. So first do it for the violet light. So what will be the violet light formula? So central fringe already tells beta y. Okay, central, oh sorry, violet, right? First case I'm using violet. So beta violet will be equal to 2 times lambda violet. What is the violet? It is 400 nanometer. 400 nanometer into uh, d. They have not given me any value of d, so leave it as it is. And the slit width is A. So ho gaya, bas. Therefore, beta violet is equal to fringe width of violet center fringe will be equal to 800 d by A. 800 d by A is the fringe width of violet light. Okay. Next, what you're going to do is try to derive the same formula for the yellow light. What will happen for the yellow light? Beta fringe width of yellow central fringe will be equal to 2 times lambda d by d. So when they're using the yellow light, they're covering half of the slit. So when they cover the half of the slit, the distance between this will become a by 2. A by 2 ho jayega, right? So this will become 2 as it is. What is the lambda? Lambda is 600 for yellow light into capital D as it is, A as it is. This small 2 will go to the numerator 2 and becomes 2 here. Okay. Now if you solve beta violet, beta yellow will be equal to 2 2s are 4, 4 6 are 2400. 2400 d by A. Ho gaya, bas. That's the end of the problem. How is the end of the problem? Because 2400 can be written as 3 into 800 d by A. What is 800 d by A? 800 d by A is nothing but fringe width of violet light. Therefore, my final answer will be equal to beta of yellow, central fringe width of yellow will be equal to 3 times central fringe width of violet. Okay, so this is the relation between violet light fringe width of central and violet fringe width of yellow. Am I clear? So let me do it very quickly again here. I'll show step by step. Okay. So we know that every central fringe width in diffraction pattern will be 2 lambda d by d. For violet light, 400 nanometer. Okay, what will happen? I'll put lambda is equal to 400. So 2 400 into d as it is into a as it is. Okay, so I'll get 800 by d. 800 d by a. Okay. And second case I'm using for yellow light. For yellow case, if you notice the question here, this half the slit is covered and wavelength is 600. So only few values will changes. So the slit will become a by 2, wavelength will become 600. And when you solve this, you get 2400 d by a, and this can be written as 3 into 800 d by a. What is 800 d by a? That is nothing but fringe width of violet light. That is fringe width of violet light. Therefore, I can easily say that fringe width of yellow light of center will be equal to 3 times fringe width of violet light. बस हो गया. Am I clear, guys? I hope I'm clear, right? Yeah. अर्थ आया. Okay, cool. So moving ahead, we are going to see one more process called diffraction. So what are the things which I learned till now? Okay, so we have learned uh, interference, we have learned diffraction. Okay, so now we are going to see polarization. Okay. Oh, before I go into polarization, I'll just tell you how the diffraction pattern looks like for different objects. Okay. So notice when you have a circular slit, okay, you take a paper and you just make a small hole or a circular hole. In this case, the diffraction patterns looks like a circular fringes. All the fringes in this case will be inside in the form of circle. Okay, see that where there is hole here, you get lot of brightness in that hole, near that hole, and nearby you get smaller fringes. You get smaller fringes, right? So when you have a point slit or a circular slit, the fringes also will be circular in nature. They'll be circular in nature. You need to remember they might ask you for as a theory question. Okay, or you should be I'm having memory of this. Okay, cool, right. And what will be the intensity? If you notice, as I already told you, the central fringe is more brighter, so it has more intensity when compared to other values. So see, and intensity dies off very quickly. I mean, after some point you can notice there is no pattern at all. But whereas in interference, I was getting this kind of pattern all the time, very equal, and it was going very long distance, but not here. In diffraction, the intensity is very high at the center, and they die out very quickly. They die out very quickly. Cool, right? And what will happen if I use a single slit and it is linear, it is a straight line. Okay, so in this case the line is in this particular path, so I got a line slit across the paper, and in this case see, you can notice one bright fringe at the center, and you can see the diffraction pattern in a linear way, like a lines, like a bands, not in a circular way but like a linear way. So this is the diffraction pattern when you get a single linear slit. Okay, cool, right? Yeah. And when you can do this also with blade. So when you do the diffraction pattern if you do the diffraction experiment by using a regular blade, razor blade, you can notice the diffraction pattern very clearly. So notice at the center or is at this rhombus shapes, you can see that there is bright dark fringes all over, right? So this is how you get diffraction in a razor blade. Okay, yeah. And so what will happen? See, in all the cases here, I'm using why I used some color here. I used blue color here. I used blue color here. What will happen if I use all the colors? I mean, like if I use white color has is a mix up of all the 7 colors. So what will happen if I use white color is I get diffraction pattern in this particular way. It's like a rainbow. Okay. And why different fringe? Here, if you notice very clearly, different colors have different fringe width. Okay, and this color separation happens because we know that beta is equal to lambda d by d. Okay, for all the colors d is same, for all the colors small d is also same, but for all the colors lambda is different. Therefore, I can say that beta is proportional to lambda, right? Therefore, as lambda changes, wavelength of light changes for every color, the fringe width changes for every color. So some fringe width is near and some fringe width is farther away. Okay, it depends on all on the wavelength. So why do I get a rainbow pattern when I use violet? Because the fringe width depends on lambda, and all the colors will have different fringe width. So colors get separated because of the different fringe widths, right? Because blue will have a different fringe width than that of a red, so red might go a little far away than blue. Okay, so in that way, you get multiple colors in this particular situations. Cool, right? Am I clear, guys? Okay, so try to remember the parameters what I've given here, right? 4 5 diagrams and the situation. So the criteria is beta is different because of lambda. Lambda is different for every color. Beta is different. Okay, so by this I can end the process of diffraction and I can start polarization. Okay, so in one class I'll be covering polarization and the resolution of light separately, but now in this 15 minutes I'll give you introduction as much as possible. Okay, so we need some time, we have to save some time because after this chapter we are going to start modern physics. After finishing modern physics it might take 5 to 6 days because in modern physics there is duality of light, there is atomic physics, there is nuclear physics. So three separate units there. It might take 5 to 6 days. So after completing modern physics, we'll complete semiconductors. Okay, again, this might take 4 to 5 classes. Okay, so by this month end, the part 2 will be over. As I already promised you, I'll be completing the part 2. And what will be left with? You'll be left with ray optics, magnetic effects of electric current and magnetism, and AC circuits. So these 3 chapters will be left. Okay, and we'll try to complete very soon in February. Okay, yeah. So okay, let me give you last one more idea before I go to polarization. Okay, which is, see, this was the interference pattern for double slit. For single slit, I get this kind of intensity or interference pattern, right? So remember that. And what are differences between interference and diffraction? So interference, what happened was when two different waves coming from two different sources, two different waves are coming and they're meeting, and I'm getting interference pattern. But in diffraction, one wave, two wavelets from a single wave are, you know, superposing and giving a diffraction pattern. So here, very simple. I have to use two slits or two sources, S1 and S2, right? And one light from S1 will come, and another light from S2. They meet and they give interference. But in diffraction, only there is single slit, and from this single slit, different wavelets within the slit will meet and get diffracted. Okay, and fringe width is constant here. All the fringe width is constant. Here, fringe width are different, and central fringe width has the highest fringe width of all the other fringes in diffraction. And here, all the maximas have same intensity. Here, maxima again have different intensity. Central maxima will have the highest intensity. Other fringes will have different intensity in diffraction. Okay, and what happens is this interference pattern has a good resolution, and you can see the interference pattern for very long distance very clearly. But in diffraction, it doesn't happen. It dies off very quickly. Okay, it is not very clearly visible. It's very smudged, not sharp. It is smudgy image. It dies out very quickly. So it is the distinction is not so clear. Cool, right? Okay, so these are the difference between interference and diffraction. Okay, so let me take some time and let me give you an idea about polarization. So what is polarization? I'll give you a very good example. Okay, so if I ask you to go in a bright sunny day, and if I ask you to watch the sunlight in bare eyes, in naked eyes, you can't watch them, right? It will be very bright. So what you can do is you can take an X-ray. You can take an X-ray sheet, right? And you can watch the sun by keeping X-ray sheet in between your eyes and the sun. So what will happen now? Initially, the sun was giving very bright light, lots of sunlight was coming, but when you keep an X-ray in between them, only few amount of light intensity will be reduced. Only few amount of light is passing, so you can watch sun a longer time. Even by this method, we are watching solar eclipse also. So it is polarization is very important in physics. Oh, I'm really sorry, guys. Again, the power was gone, so I had to, come back through my phone. I'm joining through my phone. So we'll stop the class here. Okay. Let me continue polarization, the new topic, uh, tomorrow. Okay, from the beginning, afresh. Good, right? So take care. Study well. See you all later. Bye bye. Okay. Okay. Guys.